Gujrat, we cannot hear the voice.
Oh, okay. I'm really sorry that I do not share the voice properly. So hopefully this time
of Singapore. Welcome to my talk on
This works.
Can you hear the voice? Okay, that's great.
Yeah.
Okay.
semi-supervised learning for 3D object detection. And in today's talk, I'm going to talk about two of our works on semi-supervised 3D object detection. The first work published at ICCV 19 is on cross-category semi-supervised learning for 3D object detection on RGBD data. And the second work published at CVPR 2020 is on in-category semi-supervised learning for 3D object detection on 3D point clouds. So we all know that the image-based 2D and 3D object detection tasks have always been popular and important in computer vision. Given an image of the scene that contains object of interest, for example, cars in this image here, the goal of object detection is to find the tightest bounding box around each object of interest in the scene and to correctly assign the object class label to each of these bounding boxes. In 2D object detection, the bounding box is parameterized by the object center, denoted as X and Y, and the bounding box width and height, denoted as W and H respectively. In 3D object detection, the bounding box is parameterized by the object center, denoted as X, Y, and Z, and the bounding box width, height, and length, denoted as W, H, and L respectively. There's also an additional yaw angle, denoted as theta, to denote the orientation of the bounding box around the upright axis. And in the recent years, there has been a growing interest in 3D object detection with RGBD data with the easy access to RGBD sensors. In addition to the RGB image, we now also have the corresponding 3D point clouds as inputs. Similar to image-based 3D object detection, we use the 7 parameters to parameterize the 3D bounding boxes in RGBD 3D object detection. The Froston point nets was the only existing method at that time when we look at the 3D object detection problem on RGBD input. It takes an RGB image and its corresponding 3D point clouds as input. The first part of the network applies a 2D object detector on the image to get the 2D bounding box, and then extract features from the points within the frostum formed by the 2D bounding box. The next part of the network learns a mask to segment out the points from the 3D object. Finally, the last part of the network learns the bounding box parameters on the segmented 3D points. Despite its effectiveness, the Froston point net is a fully supervised method that requires large amounts of ground truth labels for 2D and 3D bounding boxes for training. However, it is very laborious and costly to get the strong labels of 3D bounding boxes on point clouds for full supervision. This is due to the amodality and incompleteness of 3D scenes represented by 3D point clouds. So one way to mitigate the challenges of getting large amounts of ground truth labels for full supervision is to do weak supervision. In the context of RGBD data, this means that the objective is to learn 3D object detectors given only the ground truth 2D bounding boxes during training. Unfortunately, this is very challenging due to the precision needed for bounding box size and orientation. Another possible way to reduce the amount of ground truth is the in-category semi-supervised learning. In this setting for RGBD data, we are given the ground truth 2D bounding boxes for all objects, but only few ground truth 3D bounding boxes for each object class during training. A third possible way to circumvent the requirement for large amounts of ground truth 3D bounding box labels is cross-category semi-supervised learning. And in this setting for RGBD data, we are given the ground truth 2D bounding boxes for all objects classes and the ground truth 3D bounding boxes only for a few object classes during training. We use strong classes to refer to the object classes with both 2D and 3D bounding boxes, ground truths. The object classes with ground truths, only the 2D bounding boxes, are referred to as the weak classes. We deferred in-category semi-supervised learning to our second work on 3D point clouds and instead focused on cross-category semi-supervised learning in our first work for RGBD data. The main reason is because there are already existing ground truths data for 3D bounding boxes on several object classes, and we want to transfer the knowledge from this existing data to new unlabeled classes to achieve good performances. Furthermore, we choose to work on RGBD data, and it requires 2D bounding boxes ground truths because it is significantly faster to train a person to manually label 2D bounding boxes for new classes than 3D bounding boxes as shown in this paper here. And our work on cross-category semi-supervised learning for 3D object detection on RGBD data was published in this paper at ICCV 19 by my student Yu Xiang Tang. Let us first denote weak classes with only ground truth 2D bounding boxes labels as C2D and the strong classes with ground truth labels for both 2D and 3D bounding boxes as C3D. Note that the weak and strong classes are disjoint sets in the cross-category semi-supervised learning setting. Our proposed network consists of two parts. The first part is the Froston point net as our backbone network. We do full supervision on the strong classes with the same loss proposed in Froston point nets. The first loss is the instant segmentation loss to guide the network towards segmentation of the points in the frostum that belongs to the 3D object. The second loss is the 3D bounding box loss based on the anchor boxes. Since strong supervision is only possible with the strong classes, this means that the 3D object detection performance on the weak classes without ground truth 3D bounding boxes during training will be poor. Therefore, we propose a pre-trained box PC feed network to transfer the knowledge from the strong classes to the weak classes. More specifically, the inputs to our box PC feed network are the Froston point clouds features and the estimated 3D bounding box from the backbone Froston point nets. And the outputs are the box correction variable denoted as delta B hat, which serves as the correction to the estimated 3D bounding box B, and the box PC fit probability, which is the goodness of fit of the estimated 3D bounding box B. We pre-train the box PC fit network with randomly perturbed point clouds and ground truths 3D bounding boxes from the strong classes. More specifically, we emulate bad estimated 3D bounding boxes by large perturbation in P+, and good estimated 3D bounding boxes by small perturbations in P-. For training samples emulated with bad estimated 3D bounding boxes, we enforce a classification loss to output a low box PC fit probability and vice versa. Concurrently, we use a regression loss on the box correction value to give the correct 3D bounding box parameters. The pre-trained box PC fit network is then used to supervise the weak classes on the backbone Froston point nets. To this end, we introduce a fit probability loss to minimize the box PC fit probability of the estimated 3D bounding box by the backbone network from the weak classes. Note that the weights of the box PC fit network are kept frozen at this point, and hence minimizing the box PC fit probability is equivalent to improving the quality of 3D bounding box estimation from the backbone network. The final estimation of the 3D bounding boxes is taken as the sum of the initial 3D bounding box estimated from the backbone network and the box correction from the box PC feed network. We also add several regularization terms to prevent degenerate solution. In particular, we added a relaxed reprojection loss as a soft constraint to prevent large deviation of the projection of the estimated 3D bounding box from the ground truth 2D bounding box on the RGBD image. For example, the ground truth 2D bounding box is shown in green in this figure. We compute an upper bound and a lower bound shown by the bigger and the smaller blue boxes respectively. Our relaxed reprojection loss penalizes the training when the projection of the estimated 3D bounding box shown by the yellow box over here falls beyond the upper and lower bounds. We further add the box prior losses to prevent volume collapse and large deviation of the scales of the estimated 3D bounding box. Here, we penalize the network when the volume and scale of the estimated 3D bounding boxes are too far off from the mean volume and mean scale per object class. We test our in-category semi-supervised learning framework from RGBD data on the benchmark indoor sun RGBD and outdoor KITTI datasets. Here's our experimental results on indoor sun RGBD compared with the existing fully supervised 3D object detection methods. Although our method does not have access to all the ground truth data during training, we still achieve a performance that is almost 80% of the best performing fully supervised Froston point nets. We can also see that the performance of Froston point nets dropped significantly from 54 to 24.5 MAP in the semi-supervised setting. Here's several qualitative results from the indoor sun RGBD dataset. We can see that our semi-supervised method produced 3D bounding boxes that are close to the fully supervised Froston point nets. Here's some more qualitative results from the indoor sun RGBD dataset. It's interesting to note that the object orientation estimated by our methods degrades in cluttered environments. This is probably due to the difficulty in guiding the network on the regression task of the bounding box orientation without strong supervision. We also show the results on outdoor KITTI datasets on the detection of cars, pedestrians, and cyclists. We also see that our semi-supervised method can achieve good performance compared to the fully supervised Froston point nets on the outdoor KITTI dataset. One interesting thing to note is that our box PC net can also be used under a fully supervised setting to further improve the results on Froston point nets as shown in the last line of this table. Here's several qualitative results of our method on the outdoor KITTI dataset. We can see that the quality of the 3D bounding boxes estimated with our semi-supervised method are comparable to the fully supervised Froston point nets. Here's some more qualitative results of our method on the outdoor KITTI data. Similar to the indoor sun RGBD data, we can see that our method does not perform well on the orientation estimations in crowded scenes. So despite the good performance of our cross-category semi-supervised method, it still requires large amounts of 3D labels for the strong classes. Furthermore, this method also relies on 2D detectors and the availability of large amounts of ground truth 2D bounding box labels to train the 2D detector. So the obvious question here is that, can we do better? And the answer to this question leads us to the second work on in-category semi-supervised learning for 3D object detection using only 3D point clouds as the inputs. In-category semi-supervised learning means that we only use few labeled 3D bounding box ground truth labels per object class during training of our 3D object detector. Our work on in-category semi-supervised learning for 3D object detection on 3D point clouds, which we name it as SAS, was published in this paper at CVPR 2020 by my student Zhao Na. We adopt the mean teacher paradigm to achieve in-category semi-supervision with few labels per object class. We use the fully supervised VOTnet as our backbone network for the 3D object detection. We use 2 copies of VOTnet with the same architecture in our student and teacher branch respectively. Our SAS network takes the labeled and unlabeled 3D point clouds as the input. We first randomly subsample from the mixture of these labeled and unlabeled point clouds to get 2 sets of point clouds. We then apply a random transformation on one of the randomly subsampled sets of point clouds before passing this transformed point cloud into the student network. The random transformation consists of a random flipping, denoted as fx, along the x-axis, and a random flipping along the y-axis, denoted by fy, as well as a random rotation around the upright axis and random scaling of the point clouds, denoted by R and S respectively. We flipped the x-axis of the point cloud when fx is equals to 1 over here. Fx here is determined by epsilon that is uniformly sampled from 0 to 1. So if epsilon is more than 0.5, we'll flip the axis, and if it is less than 0.5, then we'll let the axis remain. The flip along the y-axis is generated in the same way. When fy equals to 1, we'll flip the axis, and when fy equals to 0, we'll let the axis remain. Random rotation around the upright axis is given by uniformly sampling the rotation angle, denoted by omega over here, from a given range of angles from -v to +v. And we set this angle to -5 to +5 degrees for the ScanNet data set, and -30 degrees to +30 degrees for the Sun RGBD data set in our experiments. Random scaling of the point clouds is sampled uniform from a range of A and B, which we set to 0.85 to 1.15 in all our experiments. We concurrently input the other set of unperturbed point clouds into the teacher network. The random transformation applied to the input point cloud is also applied to the available ground truths. We use the supervised loss from VOTnet on the outputs of the student network with the perturbed ground truths. Learning from the unlabeled data is achieved by enforcing self-consistency between the outputs of the student and the teacher networks. Intuitively, self-consistency between the student and the teacher networks means that we are transferring the knowledge of the student network learned from the labeled data to the unlabeled data. Our consistency loss consists of 3 terms. First, the center-aware consistency loss that minimizes the alignment errors of the 3D bounding box center from the teacher and student networks. For each 3D bounding box from the teacher network, we consider the closest 3D bounding box from the student network to be its correspondence. Second, the class-aware consistency loss term that minimizes the KL divergence between the class probabilities from the student and the teacher network. This is to ensure that the object class probabilities of the 3D bounding boxes are consistent between the student and teacher network. Third, the size-aware consistency loss term that minimizes the mean square errors between the sizes of the 3D bounding boxes estimated by the student and teacher networks. Finally, we do a backpropagation with the losses to update the weights of the student network. We then update the weights of the teacher network as the exponential moving average of the weights from the student network. And here's the qualitative results of our SAS compared to the fully supervised VOTnet on the Sun RGBD and ScanNet datasets. We can see that our SAS consistently outperforms the VoteNet's overall ratio of labeled data on both datasets, denoted by the red segments over here in the bar chart. It's also interesting to note that our SAS already outperforms the fully supervised VoteNet at 50% labeled data for both datasets. Here's the qualitative results of SAS compared to VoteNet on the Sun RGBD dataset. We can see that our SAS gives estimations closest to the ground truth at 30% labeled data. Our SAS is also able to detect more objects than the ground truth at 30% and 100% labeled data. Here's the qualitative results of SAS compared to VoteNet and the ScanNet dataset. We can see that our SAS gives results closer to the ground truth. In conclusion, I've presented our two works on semi-supervised learning to mitigate the requirement for large amounts of data for the important problem of 3D object detection. Our first work is on cross-category semi-supervised learning for RGBD input, and our second work is on in-category semi-supervised learning for 3D point cloud. Thank you.
All right. So that concludes the talk from Professor Kim-Hee Lee. And then I see that Professor Lee is online with us right now. So if any online audience have any questions, please speak up.
I think there's a question on the chat. Is there any link we can find the recorded video of this presentation?
Yes. So this presentation, the video has been put on the workshop website. So if you go to the schedule and under this time slot, you can see that there's a talk video link pointed to Google Drive. You can download this video and you can watch it offline. Professor Lee, if possible, could you please please give us some pointers on what will be the follow-up of of this current work in your presentation, and yeah, and can you please comment on how have you ever really test instead of just the current you are currently evaluating on Sun RGBD and ScanNet V2, and then one quick question I found on maybe this slide is that could you please give us some intuition on the performance improvement when the ratio of label data is 1 over the baseline?
Okay, so I think you have two questions here. Let me answer the first question. So I think the follow-up of this work would be, so in most of the tasks of 3D object detection, we are interested in putting the tightest bounding box around the object of interest. In this case, it's a 3D bounding box. But actually, there is still some limitation of the task itself. So because in a real, let's say in a real application where you have a robot trying to grasp something from the scene, the bounding box itself is not precise enough. So a follow-up of this work would be maybe to look into the instance segmentation, 3D segmentation of the object. And this would be a more precise way of object detection. So it could also be, I mean, it could be first maybe we should look at the fully supervised method to do this, and then maybe progress to investigate the semi-supervised method of doing this. And a more challenging way of looking at the non-fully supervised techniques would also be weakly supervised and even to the extent of self-supervised. But actually, this is weakly supervised and self-supervised. They are very challenging because in this case here, we are interested in looking at not only the object location, but the object size and the object orientation. So in our experiments, actually, we tried to look into weak supervision initially, but this was actually quite challenging because of the precision that is needed for the object orientation and the object size. So this is especially the object orientation. This is the one parameter which we regress from the deep network, and we realized that without the full supervision or without any supervision at all in the weakly supervised case and the self-supervised case, this is very difficult to tell the network, to train the network in recognizing or to try to regress that number for the orientation. Okay, so, but I think that the follow-up work would be really to look into this, although it's a much more challenging problem, and the instance level segmentation for 3D object detection. So regarding your second question, the insights to why at 100% training, our SAS is still able to improve the result. The reason is because of the self-consistency. So there is a self-consistency loss. We also applied that self-consistency loss on the full supervision, I mean on the fully labeled data set. So you can think of it this way, that because of the random perturbation between the student and the teacher network, even though there is a self-supervision, that is just one part of it where we fully supervise that part. But we actually, you can think of it this way, that we are actually augmenting the data with the random perturbation. So in addition to the original full supervision, we have an augmented set from the from the self-consistency part, from the random perturbation, and that part actually gives further supervision to the network, because we realize that at 100% labeled data, we are still able to improve the performance by quite a bit.
I see, that makes sense. Thanks for your response. Yeah. Okay. And is there any other question from the live audience? If not, then let's thank again for Professor Lee's presentation. And then I would like to conclude this workshop by saying that we really appreciate that for the attendees to attend from starting from early morning Pacific time until now. And then all the videos are all available on the workshop website for you to download, and you can watch it offline for if you need them. And then we really appreciate your feedback. If you see, we know that this is an unprecedented time to host a workshop, and especially everything is virtual. So, but we still appreciate the feedback from your experiences of this workshop. And the reason why we receive a lot of requests about whether there is call for papers or not, and in the end we decide that there's no call for papers. The reason is that according to our past workshop organizing experiences, we have experiences of organizing the workshop with versus without call for papers. And then from the feedback of the attendees, we find that most attendees feel like they gain more insight from the speakers, the keynote speakers, instead of just the accepted papers presentation. However, we do hear from the request of a call for paper. So I'm excited to announce that actually recently I already have another CVPR 21 workshop proposal entitled the second workshop on fair, data efficient, and trusted computer vision that will be held in CVPR 2021 this year. And there will be a call for papers. And for that workshop, it will be a 1 full-day workshop during June 19th to 25th. The date is still to be announced by the CVPR 21 official. And then more details will be put on this website showing by this QR code and then the website, and for the announcement of call for papers. And currently we already have a few keynote speakers lining up, as you can see by these diverse sets of speakers in terms of their expertise. And so I encourage everyone to attend to this CVPR 21 workshop, and then hopefully see you there. And then hopefully we will try to continue to host this workshop in conjunction to WACV annually. So hopefully you can stay with us and then continue supporting, participating. And at the end, I sincerely appreciate everyone's support and participation to make this workshop happening. Thank you very much. And that concludes our workshop in WACV 21, and see you in WACV 2022 then.